minus 0.28 volts. After that, nickel, here I am writing nickel plus 2, 798 you are getting, and the E naught you are getting is minus 0.25. Copper to copper 2 plus, we are getting 921, the sum of the values. E naught is plus 0.34 volts. Finally, the last element, zinc. The net energy change is 711 and E naught is minus 0.76. Now, actually, we need not by heart this entire table, add the values, subtract the hydration energy value, and by heart the E naught values, but you should have an idea. In the first series of the D block, there is only one element with a positive SRP value, that is copper. Copper is having a positive SRP value plus 0.34 volts. Why all others are having negative SRP values? Why the copper is having a positive SRP value? See, the net energy change is too high here. 921 kilojoule per mole. The values are all in kilojoule per mole. So, first you have to write that. In case of Cu2 plus 2 electrons, Cu E naught is equal to plus 0.34 volts. Indicate that copper cannot liberate hydrogen from acids. While WHILE, while all other elements mentioned in the series, can liberate hydrogen from dilute acids. So from this you understand one point in electrochemistry also, that only metals with a negative SRP can liberate hydrogen from dilute acids. Copper with a positive SRP value cannot liberate hydrogen from dilute acids. It's a very, very, very important point. The second point, copper can only react with very strong oxidizing agents. Very strong oxidizing agents like concentrated sulfuric acid and concentrated nitric acid, in which the acids are reduced, but hydrogen is not, in which the acids are reduced, but H2 is not evolved. Suppose any student can, or any doctor can recall, in the P block, we discussed this point. Cu plus HNO3 dilute. Cu plus HNO3 concentrated. Both are very much recorded in your notes. No, NO. N2O come from zinc. So here cupric nitrate, CuNO3 twice plus NO plus H2. Means here N is reduced from +5 to +2. Copper is oxidized from 0 to +2 state. It's a redox reaction. This also we discussed. Very good. Cupric nitrate plus NO2 plus H2. Balancing part you can later see. +5 to +4. This is reduction. 0 to +2. This is oxidation. The positive SRP value of copper indicate the positive SRP value of Cu2 plus indicate that the sum of enthalpy of atomization IE1 and IE2 indicate the sum of enthalpy of atomization IE1 and IE2 are not compensated by the enthalpy of hydration. Next point, higher the negative value, of SRP, greater is its tendency to undergo oxidation and greater the reactivity, and greater is the ability to act as anode in an electrochemical cell. Suppose if we see the entire series, which is having highest negative value of SRP, titanium 2 plus. This is having highest negative value of standard reduction potential. Higher the negative value of SRP, easy it undergoes oxidation, means it is a good reducing agent. The one which is undergoing oxidation will act as a reducing agent. It supplies electrons. Means titanium supplies electrons more easily than any other element in the first D block series. When it loses electrons and undergoes oxidation, when you connect this titanium electrode to other electrode, it has more ability to act as anode. For example, you all know the Daniel cell, which is an example of voltaic cell. We take Daniel cell. What do we take? A zinc plate is dipped in zinc sulfate. This is zinc sulfate aqueous solution. This is copper electrode. This is copper sulfate aqueous. Let us take 1 molar of both. Here the reverse occurs. The copper 2 plus ions from the solution, the electrons from the zinc plate pass through the wire, external wire, and comes to the copper electrode. Here the copper 2 plus ions undergo reduction to copper. From solution they undergo reduction and deposit as copper. So copper is deposited on the plate. Finally the copper plate weight increases, means more copper is deposited. Here if you take the values, the E naught value of Zn2 plus, E naught of Zn2 plus slash Zn is equal to minus minus 0.76 volts, whereas E naught of copper Cu2 plus slash Cu is equal to plus 0.34 volts. So this is a very easy comparison at this juncture. The negative value of SRP indicate that it is undergoing oxidation. Loss of electrons is called oxidation. Addition of electrons is called reduction. So this is called oxidation half cell. What is this? Reduction half cell. The two half cells are externally connected by a wire. Through that wire, whatever the electrons left on the zinc plate, why zinc plate is left with electron? When each zinc atom undergoes oxidation, it gives 2 electrons. The 2 electrons are left on the plate. That's why here anode is given negative sign. It is anodic half cell. Why it is called anode? Because oxidation occurs. Oxidation always occurs at anode. Reduction always occurs at cathode. This is cathode. So, but why it is given negative sign? Because of the oxidation of zinc into Zn2 plus, whatever the electrons it is losing, they are left on the plate. So 2 electrons accumulated on the plate. So overall plate charge is negative sign, but it is anode. Actually anode is positive. But in electrochemical cell, exactly the reverse. Anode is negative, cathode is positive. Why it is positive here? Because the electrons are dragged by copper 2 plus to undergo into reduction. So it is electron deficient, this plate. This is electron rich plate. This is negative, this is positive. This is a typical electrochemical cell. So why I brought this point here? To understand you that one. Yes. To understand you that the negative SRP value, which is also called E0 value, greater the negative value, greater is the metal act as undergo oxidation and act as anode, and easily it undergoes corrosion. Greater the negative value of SRP, greater the tendency of that metal to undergo corrosion. Corrosion is nothing but chemical oxidation. Corrosion is nothing but chemical oxidation. That's why what the shipbuilding units, what they do. When the ship is completely manufactured, when it is about to enter into sea waters, ship is a huge object. Some ships are very big. India has acquired one Russian ship, aircraft carrier. Its name is Admiral Gorshkov, Russian name. But when it enters in Indian waters, it is named as INS Vikramaditya. It is stationed in Karwar port in Karnataka. Actually, the ship is a game changer. Because the ship entered into Indian waters, the enemy people surrounding our country become alert. Oh, now they have a nuclear powered aircraft carrier. The size of the ship is, it is like a 7-floor building. And the ship deck, the area of the deck of the ship, is more than that of a football ground. You can imagine the size of the ship. So ships are very huge objects. Actually, crew members required to operate is also very high in number. And the food they consume every day, lot of food they have to prepare. Only for 48 students in SIRD, preparation of food is a Herculean task. Isn't it? So, that much organizational things will be there in the INS Vikramaditya. India has acquired it for 100-year lease from Russia. The ship cannot move with normal fuels like petrol, diesel, ship cannot push further. It is powered by nuclear power. So now the aircrafts can take off from that ship, land on the ship. It is an aircraft carrier. Okay, this is all one side. Second side is seawater contains many salts, dissolved salts. These salts easily corrode the metal of the ship. So metal, the outside of the ship metal is always in touch with water. No sir, every day evening the ship again comes to the dockyard. It will again fully subjected to cleaning, and again we push it back into the sea. No. Once the ship enters into the sea, its lifetime they predict, engineers predict 100 years, 150 years or 40 years. Up to that lifetime it remains in the sea waters. Once that lifetime is over, it is brought to the dockyard, removed from there. Wreckage plants will be there near India. We have one wreckage in Goa. Goa ship wreckage is there. They break the ship, take the iron, any metals, melt and again reuse. That is the. So ship, when it is present in sea water, it should not be corroded. To prevent corrosion, what they do, the ship, this is asked in the 2003, I think, AIEEE first time introduced. This is asked. The hull of the ship or the body of the ship are connected with the blocks of magnesium. So if you take the reduction potential of magnesium, gives Mg. The E0 value we have to take. And just now we discussed Fe2 plus 2 electrons gives Fe. Its E0 value just now we have seen. But E0 of Mg2 plus we don't know. Yeah? Oh, very good. Minus 2.66 volts. Very good. Okay, whatever it is. Now, my opinion is, when compared to this negative value, this is having higher negative value. So, to further understand the point which now we claimed, higher the negative value of SRP, greater is the tendency to undergo oxidation or corrosion. Oxidation and corrosion both are same. So when you attach the body of the outside body of the ship, blocks of magnesium, in sea water, when iron is about to corrode, magnesium blocks say, my dear iron, wait. We are here to protect you. We undergo corrosion first, because we are having higher negative value of SRP, and they sacrifice. Magnesium blocks undergo oxidation, corrosion, and prevent the ship body to undergo corrosion. This is called sacrificial method of prevention of corrosion. One is sacrificing on behalf of the other. Here, in case of ship and magnesium, who are sacrificing themselves to prevent the corrosion of the body of the ship? Magnesium is undergoing corrosion, because magnesium is having higher negative value of SRP when compared to the negative value of SRP of iron. So you should understand that higher the negative value of SRP, greater is the tendency to undergo oxidation, greater is the tendency to undergo corrosion, greater is the tendency to act as anode in electrochemical cells. So all these are valid points. So this is called galvanization actually. Galvanization is also, just now we discussed galvanization also. Actually iron is coated with zinc. Fe plus 2 electrons gives Fe. E naught is equal to minus 0.44 volts. Zn 2 plus E naught is equal to minus 0. So between these two, here we are comparing iron and zinc. Who is having higher value, higher negative value of SRP? Yes. So Zn is having higher negative value of SRP. That's why when zinc and iron are together present, who is ready to undergo oxidation or corrosion? Zinc but not iron. That's why the water pipelines, the municipalities, they make water pipelines underground. In underground also soil, moisture, many things corrode the pipes. To prevent the corrosion of the pipes, they use galvanized iron pipes. What is meant by galvanization? Coating of zinc over iron is called galvanization. Coating of Zn over iron to prevent corrosion is known as galvanization. And the corporation, municipal corporation people, they also do an extra, or not only they coat zinc over the iron pipes to prevent corrosion, they also take one more precautionary measure. After every few kilometers, the pipeline is attached with blocks of magnesium. Because they can't dig the entire pipeline route and see where corrosion occurred. They can't check the pipeline every day. Because once it is laid down, it runs for hundreds of years. If any accidental galvanization is missed at a particular point, corrosion occurs, the pipe breaks, water leakage comes, and all bacteria will go into the drinking water, that is, virus also goes. That is the root cause for the jaundice. Jaundice is caused by water pollution. So your liver dysfunctions, hepatitis virus. Hepatitis, many viruses are there. Hepatitis C is the most common. Hepatitis B is most dangerous, but it only occurs through blood contamination. General hepatitis is C, waterborne disease. The person will, eyes become yellow in color. Urine also become yellow in color. So many symptoms. There is a loss of appetite. Person can't take food. When all these symptoms are noticed, doctor recognizes that it is hepatitis. And only simple rest with a little liver protection medication. Because you can't kill the virus. Virus is overpowered by immune system. So slowly your body develops immunity and kill the virus. That is hepatitis C. Of course, hepatitis B, you have to go for vaccination. There is no other go because it is somewhat dangerous. So, here, as we are seeing the standard reduction potential values of the M2 plus ion plus 2 electrons gives M solid. So we have come to a conclusion the irregularity of the SRP values indicate that the energy changes are also irregular. What are the energy changes involved? It is enthalpy of atomization, the positive sign, IE1, which is also positive sign, endothermic, IE2, which is also positive sign. So three positive values are there. One, enthalpy of hydration, which is a negative sign value. If you sum up all these values for the entire first row of D block elements, those values, some of the values irregularly vary. And in case of copper, it is 960 something. 9. So highest value you are getting copper. That's why it is having positive SRP value plus 0.34 volts. That's why copper cannot be easily oxidized. That's why copper vessels we use regularly. But copper vessels don't oxidize. But copper develops a green color layer over it. It is not oxidized product. It is due to Acetobacter, a bacteria, which oxidizes when you prepare some sweet in a copper vessel. The sweet layer attached to the copper vessel is fermented by the Acetobacter bacteria into acetic acid. So the sugar content is converted into acetic acid. First it is fermented to alcohol. Alcohol is further oxidized to acid. This acetic acid reacts with copper to form copper acetate. Plus some basic copper carbonate. These two compounds are formed and forms as a green layer on copper vessels. This will change. Actually, this is written as CuOH twice dot CuCO3. I will separately write. It is CuOH twice plus CuCO3 plus CH3 COO twice Cu. Cupric acetate, cupric carbonate, cupric hydroxide. This mixture form as a green layer on copper vessels. That's why when copper vessels are not properly washed, food poisoning occurs. Generally, this happens in our country. In big temples, they make this sweet items with rice in copper vessels and serve to the devotees as prasad. So devotees comes in lakhs and lakhs every day. Huge temples. So many devotees visit. They offer this prasadam, free, eatable, sweet content. So if the temple authorities are not properly cleaning the copper vessel, the green layer, which is a mixture of three compounds, cupric carbonate, cupric hydroxide, cupric acetate. This is called with a special name called verdigris. So verdigris is a green layer formed over on the copper vessels. It causes food poison. All the devotees after taking the prasad, they will develop vomitings, lose motions and all these. Doctors easily understand it is due to food poison and treat in hospitals. Nothing to worry, it is not, it won't create any deaths, but stomach upset and all these things will happen. Right, one more point, which is having the lowest SRP value in the entire series. Lowest means highest negative. That is titanium. Titanium with minus 1.63, that is having highest negative value, means lowest SRP value. Correct? And the highest is by copper, plus 0.34. But you see, the lower negative values of nickel and nickel is minus 0.25, 28, 25. Cobalt is minus 0.28. So NCERT text also have given one point about that. Please read that point, that also will make a note. Why nickel and cobalt? Why nickel is having the low negative value of SRP? They have given one point. Its enthalpy of hydration is less or more, something is given. We should not leave anything left. That's why I am pointing that point. Why nickel is having minus 0.25? Due to its high hydration enthalpy or low hydration enthalpy, they have given one point. You can't find? It is there in textbook. Find? Anyone find?
Sir, one line is there. The value of E0 is for nickel are more negative than the expected from the trend.
The value of Ni2 plus
More negative than expected from the trend.
due to
Increase in the sum of first and
that's point. That point only I want. Increase in
due to increase in the sum of first and second ionization entropy.
which is not compensated by. Okay. No, that point is not that much important. Okay. Regarding M3 plus 3 electrons gives M. Table 8.2, I think. 2-3 points also we have to discuss here. Table 8.2. There is first, second and third ionization enthalpies, hydration, E0 values are given. So what are the E0 values for this?
So here it is written changes from +3 to +2.
+3 to?
+2.
Okay, +2. That is given, okay. Not directly metal. So M3 plus electron gives M2 plus aqueous. What are the E naught values? First one
It is not given for this candidate.
up to
From titanium to cobalt
not given.
given, and scandium, nickel, copper and zinc is not given.
Oh, they don't form. Okay. What are the given? Please mention.
Titanium is minus 0.37.
So titanium 3 plus electron gives titanium 2 plus. What is E naught?
0.37 minus 0.37.
37. Next.
Vanadium is minus 0.26. Chromium minus 0.41. Manganese plus 1.57.
1 by ferric to ferrous. D5 4s1. And chromium 2 plus 3d4 4s0. This is case 1. And Mn 3d5 4s2. Mn 3 plus 3d4 4s0. This is case 2. A very important question they are asking on this. Both Cr2 plus and Mn3 plus have similar configuration. Both Cr2 plus and Mn3 plus have same 3d4d4 configuration. But one will act as oxidizing agent, one will act as reducing agent. This is a very, very important question. Suppose in case of manganese 3 plus, if you add one electron, it become Mn2 plus and its configuration become 3d5 4s0. If you remove one electron from minus electron, it becomes Cr3 plus, or minus electron, here I write like this, better you understand, with 3d3 configuration. Here one is losing electron, one is gaining electron. Though both have initially same d4 configuration, this is having d4, this is also having d4. So chromium 2 plus, what it is doing? It is losing an electron to become Cr3 plus, means it is undergoing oxidation. The one which undergoes oxidation acts as reducing agent. So Cr2 plus is acting as a reducing agent by losing an electron, and Mn3 plus is acting as oxidizing agent by taking an electron, though both have similar configuration. The reason is very simple. By losing an electron by Cr2 plus, when it becomes Cr3 plus, the configuration 3d4 become? Yes, the configuration becomes Cr3 plus. So with a D3 configuration, so in the crystal field theory, when the 5 d orbitals split into two sets, and if the T2G set is half filled with a D3 configuration, it is stable. So why chromium 2 plus is losing an electron and acting as a reducing agent to get stable half filled T2G configuration. While Mn3 plus, why it is gaining an electron to make its configuration into D5, which is half filled. So both are initially having same D4 configuration, but one is acting as a reducing agent, means it is losing an electron. One is acting as an oxidizing agent by accepting electron. So same point please mention. Cr2 plus and Mn3 plus. Cr2 plus and Mn3 plus have same D4 configuration. Have same D4 configuration. But Cr2 plus acts as a reducing agent by losing an electron. Cr2 plus loses an electron and acts as a reducing agent so that its configuration become D3. So that its configuration become D3, in which the T2G set is half filled. In which the T2G set is half filled, while Mn3 plus accepts an electron Mn3 plus accepts an electron and acts as an oxidizing agent. In which it is getting a stable half filled D5 configuration. In which it is getting a stable half filled D5 configuration. Next, If you take the F block, in which we take lanthanoids or lanthanones. So lanthanum, cerium, praseodymium, neodymium, promethium, samarium. Europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, ytterbium, lutetium. So if you write the atomic numbers 57, 58, 59, 60, 61, 62, 68, 71. These are lanthanoids or lanthanones or rare earth elements. Actually, all these, for many years, they confused the scientists because their properties are very much similar to each other. When properties are very close to each other, scientists believed that all of them as one single element because their properties are very, very close. That's why there is a question, or we can create a question. Separation of lanthanoids is very difficult. Separation of lanthanoid elements is very difficult. That is assertion. If reason I give, due to very close or very close similarity in properties, separation of lanthanoids is very difficult. That is assertion. Reason, due to very close resemblance in their properties. If this question is given, the option will be 1. That is, both assertion and reason are true, and reason correctly explain assertion. Actually, lanthanum, scandium, yttrium, lanthanum. 3d1, 4s2, 4d1, 5d1, 6s2. We follow your NCERT book only in configuration. Cerium. Cerium is given 4f, 5d, 6s. This is common for all. You have to fill. Because different books are giving different versions. We follow our NCERT book. Okay, cerium F subshell. Please refer your text. F subshell is filled or F0? F1, 5d1, 6s2. Now cerium is 58. Here we discuss one more very important point. When cerium loses 4 electrons, it becomes cerium 4 plus 4 electrons, and it will get stable xenon configuration. Cerium is ready to form Ce4 plus because it is going to get stable xenon configuration. Okay, in praseodymium, F2, neodymium, F4. After F2 it is F4. F4, 0, 6s2. After F4 next F5. Next F6.
0, 0.
So in the sodium there is low electron confinement.
Means it is 4F3 they go. That's why I asked you. So after immediately 1, 2, 3 jump. So lanthanum is a D block element. Lanthanum is not an F block element. But the followers of lanthanum from cerium to lutetium, they are F block elements. Lanthanum is a 100% D block element. Definitely europium, 4F7, 5D0, 6s2. Again F7 will continue. So here 2 times F7 configuration. Because F7 is stable half filled. That's why it is continued in the next element also. Is it F7 to F8 or F9? Again 4F10. Is it 11? Oh, here 4F13, 5D0, 4F14, again 14. The most common oxidation state is +3. Common oxidation state is +3. So you should understand which subshell is filled in lanthanoids. 4f is filled with some exceptions. What is the gradual filling? 4f subshell is filled. Is the 4f is in the outermost shell? The answer is no. First, second, third, 4, 5, 6. There are 6 shells in lanthanoids. 6s2 is here. Here 5d, 0 to 1. Sometimes 0, sometimes 1. But the 4f sublevel is gradually filled. This is 4f. This is called outermost or ultimate. Ultimate shell, which is called nth shell. The last but one, it is called penultimate. Penultimate shell, which is called n-1 shell. Second from the last, this is called anti-penultimate shell. Which is also called n-2 shell. Now the electrons that are entering here, up to 14 electrons it can accommodate. There are 7 boxes. Each box is an orbital. Orbital can accommodate 2 electrons. So 7 boxes, 7 into 2, 14 electrons it can accommodate. That's why the last element, lutetium-71, is 4f14, 5d1, 6s2. So the f orbital starts filling from cerium 58, 4f1 started filling, and lutetium, the series ends. But these f orbitals, which are in the anti-penultimate shell, they can't stop the nuclear attraction reaching over here. Nucleus want to extend its influence to the last electron. When nucleus want to extend its influence up to the last electron, the electrons in between the nucleus and the outermost electron act as a screen or shield. And the shielding effect prevents the nuclear attraction. But here, the f orbitals, because of their peculiar shapes, f orbital shapes, f orbital are complex shape, are in complex shape. There are 4 lobes above and 4 lobes below. This is f orbital. So XYZ axis, some lobes are above, some lobes are below. You can't describe the shape. You can say it is a 4-fold dumbbell. So this complex shape of f orbitals or peculiar shape of f orbitals, they can't prevent the nuclear attraction reaching the outermost electron. So they cause poor shielding effect. So because of this poor shielding effect, the nucleus crosses all the barriers, all the shields, all the screens, and reach the outermost electrons and strongly attract them. That's why there is a contraction in size, which we call lanthanoid contraction. But lanthanoid contraction is more pronounced or more visible in the tri-positive ions. Write an assertion reason question. Lanthanoid contraction is more pronounced in their tri-positive ions when compared to their atoms. Lanthanoid contraction is more pronounced in their tri-positive ions when compared to their atoms. You know, tri-positive ions means they should lose 3 electrons, isn't it? When they lose 3 electrons, 2 outermost s electrons, 1 d electron, if they lose, so this part is over. These are over, these are over. When these electrons are lost, it becomes Ln3 plus. Ln is any lanthanoid. So Ln3 plus is not having S2 or D1. Only the outermost shell become, 4th orbit become the outermost shell. Because these 2 shells are not having any electrons. So why in the tri-positive ions the contraction is more visible or more pronounced? So the reason we are giving. One F electron cannot shield the other F electron within the same subshell due to their peculiar shapes. One F electron cannot shield the other F electron within the same subshell due to the peculiar shapes of F orbitals. So when these 3 are lost, when these 3 electrons are gone, within the F sublevel, the electrons are entering up to 14 electrons. One F electron cannot shield the other F electron because of that peculiar shapes. That's why the nuclear pull will be more. When shielding is not there, nucleus can strongly pull. That causes more and more shrinkage of size. That's why I ask you to see this diagram in your textbook. This is size versus atomic number. You will get a curve like for M3 plus ions or Ln3 plus. I think this curve is given. Is it given? Cerium 3 plus, Pr 3 plus, neodymium 3 plus, samarium 3 plus,
PF also. Astar and DPF.
okay, promethium 3 plus, samarium 3 plus, europium 3 plus, gadolinium 3 plus, terbium, dysprosium, holmium, erbium, thulium, ytterbium, finally lutetium 3. Not found? Okay. I'll give those points. I'll make a note of them and you are searching with a difficulty. So the size of dry positive ions vary much. Write one more point. Because of lanthanide contraction, the following periodic trends are affected. Number 1, zirconium and hafnium have similar size. Atomic sizes of 4D series and 5D series are similar. Ionization energy of 5D series is greater than ionization energy of 4D series. This is one more point, very, very important. We already discussed twice, thrice. In periodic table we discussed, in D block we discussed, in F block we discussed. 3 times these 3 points are repeated. Next, one more textual data point. The first members of lanthanide series resemble calcium, I think. Please see. The first members of lanthanide series resemble to the properties of calcium, and the heavier members of lanthanide series resembles aluminium in properties. Please mention that point, it is also very important. The first members of lanthanide series resemble calcium in their properties. And the heavier members of the lanthanoid series resemble aluminum in their properties. Next point. Actinoid contraction is more than lanthanoid contraction. So 90, 91, 92, 93. After that, plutonium should come. '94. So actinium, thorium, protactinium, uranium, neptunium, plutonium, americium. We'll change some. Americium, curium, berkelium, californium, einsteinium, fermium, mendelevium, nobelium, lawrencium. 96, 97, 98, 99, 100, 101, 102, 103. Yes. So this is 96. 97, 99, 100, so these elements, actual actinium is 6d1 7s2. Now 5f 6d 7s. These are common. You have to fill with the different anomalous situations. So thorium, please refer your textbook. Is F sublevel filled or not? 0. So it becomes 6d2. Protactinium. So 5f2.
D1,
Uranium.
F3, 1, F6,
F 3 to 6.
4,
Neptunium, plutonium.
F6, 6. D0.
7.
S.
7 will repeat. 5F7, 6D1, 7S2. Curium. Next, berkelium. 7 to 9 jump.
7.
Californium.
F10. D0.
Einsteinium.
F11.
Fermium. Thirteen. 13 or 14?
13.
The last two will be 14, 14. Lawrencium 5F 14, 6D1, 7S2. So look at the elements once again. Actinium 89, thorium 90, protactinium 91, uranium 92, neptunium 93, plutonium 94, americium 95, curium, named or Madam Curie, berkelium, actually University of Berkeley in California. From that it came berkelium. Next is californium, einsteinium, fermium, mendelevium, nobelium, lawrencium. Actually, Lawrence Berkeley National Laboratories, both are in California, very famous labs in the entire world. So based on that the names came, but actually here the common oxidation state again +3, like lanthanoids, actinoids also show +3 as common oxidation state. Actinoid contraction is more than lanthanoid contraction. Actinoid contraction is more than lanthanoid contraction, as 5F orbitals cause less shielding effect than 4F orbitals of lanthanoids. So you please retain this. After the break we will continue.
Minus 2 is more than so. Tapi memang boleh sih. Nah, engineer kan? Engineer.
Actually, this UUB, un by M, that we have already discussed under the name of Copernicium. So total 4 series, each series 10 elements, 40. But in the first series, we are given some anomalous situations at chromium and copper. This is one point, chromium and copper. So this is the only point, only 2 elements, chromium and copper. In the second series, see, it started with 4D1, 4D2, niobium 4B4, 4D4. But that is not that much molybdenum like chromium. Chromium and molybdenum belong to same group. It is 4D5, 5S1. But look at palladium. Palladium you have 5S0, 4D10. So here this you have to note down. Palladium configuration 4D10, 5S0. The last two are similar. Here very interesting. The d orbital start filling in the third series. 5D1, 5D2, 5D3, 5D4, 5D5, 5D6, 5D7. Up to 7 it is common. At the platinum configuration you mentioned. Platinum 78, 5D9, 6S1. 5D9, 6S1. The first series and last series are similar. See, first series D subshell 3D1 to 3D8. Last two are 10-10. Here also last two are 10-10. First and last are similar. This is regarding configuration. Actually, this point we discussed only at one place. Why D block elements easily form alloys? Because of similar size, similar crystal structure I mentioned. So in the first series, scandium is BCC, titanium is BCC, vanadium is BCC, chromium is BCC, again iron is BCC. Most of them are BCC type, except BCC means body centered cubic lattice. What is HCP? Hexagonal close packing. CCP means cubic close packing. Here they mentioned body centered cubic, hexagonal close packing, cubic close packing. A typical metal structure is X, that is mercury, zinc, cadmium and mercury. This graphs also we discussed why manganese suddenly shows a fall in melting point up to chromium. Again copper and silver, these three are copper, gold, silver, very low melting points. In the second series also, technetium shows a lowering of melting point. Up to molybdenum it increases, technetium suddenly there is a decrease. What is the reason for it? D5 configuration. So manganese with D5, technetium with D5, here D5, here it is 4D5. So half-filled d orbitals do not effectively participate in metallic bonding. Copper, silver, gold, very low melting points. Because of full-filled D10 configuration. With the D10 configuration. So it is obvious to see D5 and D10 configurations cause low melting point because of the non-participation of full-filled and half-filled d orbitals in the melting points. Now coming back, this table also we discussed just now. Here, this graph also yesterday we discussed. Regarding ionization enthalpy, you write one point. The ionization enthalpy of D block elements are higher than S block but lower than P block. The ionization enthalpies of D block are higher than S block but lower than P block, and within a series the IE increases from left to right. The IE increases from left to right. With increase in nuclear charge, and also similarity in sizes. Here three important questions are there. Why chromium and copper have abnormally high IE2? So this all of you know. Chromium and copper, why they have IE2 very high? Because of half-filled and full-filled orbitals. Next, in 3D series, the enthalpy of atomization of zinc is the lowest. Why? Due to the D10 configuration, the d orbitals are not effectively participating in metallic bonding. Why copper, nickel, zinc generally do not show oxidation state greater than 2? So write these 3 points. In 3D series, the following anomalies are noted. Number 1, CR and Cu have IE2 very high. Chromium and copper have very high IE2, second ionization enthalpy, due to their stable half-filled and full-filled orbitals. Due to the presence of stable half-filled and full-filled orbitals. Next, second point, why Zn has the lowest enthalpy of atomization? Zn has the lowest enthalpy of atomization due to weak metallic bonding, as the fulfilled d orbitals of Zn do not effectively participate in metallic bonding. Next point, copper, nickel and Zn do not show more than an oxidation state of +2. Do not show more than an oxidation state of +2 because of their high IE3 values. Because of their high IE3 values. Manganese and iron, which has higher IE3 value, between manganese and iron, which has higher IE3 value, and why? So answer is Mn, 3d5 4s2. After losing 2 electrons, D5 is half-filled stable configuration. So answer is Mn due to the stable D5 configuration in its +2 state. In 3D series, which element has the highest IE3 value? The answer is Zn. Zinc will have, see the table 8.2 in your textbook, 8.2. What is IE3 value of Zn?
3,837.
Is there any element having that much high value? So Zn has highest IE3 value in the 3D series. Similarly, compare the IE3 of manganese and iron from the 8.2 table.
Iron is 3,260 and manganese is 3,260 and iron is 2,960.
So manganese is having more because manganese configuration in +2 state is 3d5. Half-filled d orbitals. Removal of third electron require very high energy. This fact file, scandium does not exhibit oxidation at a +2, correct? Because it directly loses 3 electrons and get a stable argon configuration. Titanium 2 is more stable than titanium 3 and titanium 4. Scandium, titanium 3d1, 4s2. Uh, 3d2, 4s2, sorry. 3d2, 4s2. So titanium 2 is more stable than titanium 3 and titanium 4. So this point we already discussed. Third point. In the 3D series, actually up to manganese, the highest oxidation state increases. It reaches up to +7. But after manganese, from iron onwards, the higher oxidation state decreases due to the pairing of d electrons in the d sublevel. So iron can exhibit maximum 2 and 3, cobalt also 2 and 3, nickel only 2, copper 1 and 2. Why they are showing lower states? Up to manganese it is increasing up to +7. Manganese, iron, cobalt, nickel, copper, zinc, they are decreasing. The higher state is not visible. Maximum iron can show +3 in ferric. It shows +2 in ferrous. It shows +1 in brown ring complex. It shows 0 in carbonyls. Yesterday we discussed all these points. How can it show that change in oxidation different from value? This one. Actually, this point in P block and D block comparison, see this para, if it is visible. Or I will explain in a very nutshell. Suppose if you take the oxidation states of P block. Nitrogen shows +3, phosphorus +5. So nitrogen to phosphorus, the difference in oxidation state is 2 units. But in D block, it is not like that. They show difference in oxidation state by 1 unit. Because the D subshell is filled with 1 electron each. So look at the vanadium. Vanadium shows 2 oxidation state, vanadium 3, vanadium 4, vanadium 5 also. Vanadium 5 we discussed, V2O5 or VF5. So vanadium can show up to +5 in V2O5 and vanadium pentafluoride, VF5. Vanadium can also show VO with +2 oxidation state or VO2 plus with +3 oxidation state. So it shows +2, +3, +4, +5. Each oxidation state differ by 1 unit. Whereas in P block non-transition elements, the oxidation state shows a difference of 2 units. That's why we already discussed why bismuth do not show +5 in 15th group due to inert pair effect, whereas its previous elements show +5. In 16th group, sulfur, selenium, tellurium show +6, but polonium shows only +4. So in the carbon family in the 14th group, carbon, silicon, germanium, tin, they all show +4. But tin and lead also show +2 due to inert pair effect. So that is the meaning of this pair, example 6. See this. This some points you may note down. Formulae, the small English mistake. There is no formulas, formulae. So formulae of halides of 3D metals. +1 halide is only present in cuprous halide, CuX, or CuCl, or Cu2Cl2. But dihalides or bihalides, +2 state, many are shown there. TiF2 or TiCl2, vanadium dichloride, chromium dichloride. X can be FCl, Bri. Like that, dichlorides. Almost all elements are forming dichlorides or dihalides. This entire row. TiX2, VX2, CrX2, MnX2. So many are there. But trihalides, C, TiX3, VX3, CrX3, MnF3, FeCl3 we all know, cobalt trifluoride also we know. Tetrahalides you see, TiX4, VX4, CrX4, MnF4. Pentahalides VF5, CrF5. Only hexahalides CrF6. This point yesterday I discussed under a different concept. I mentioned though fluorine brings highest oxidation state for a given element, in D block oxygen will bring that highest oxidation state because of P pi D pi multiple bonding. Same point here, there is no +7 oxidation state halide. Though manganese can exhibit +7, you don't have MnF7 or MnCl7. Rather you have KMnO4 where Mn is +7. So here instead of halides the oxides show highest oxidation state. See here, oxides are given. You have only one +1 oxide, that is cuprous oxide. Cuprous oxide is red color, red precipitate, which you studied in your aldehydes ketones. When aldehydes and ketones, when they want to differentiate, for differentiating aldehydes and ketones, we use Fehling's reagent or Bendix's reagent. So Fehling's or Bendix's reagents are cupric sulfate, blue color solution. So when aldehyde is mixed with Fehling's or Bendix and just warm it, immediately we will get red cuprous oxide. So how aldehyde group is easily recognized in the lab? By using Fehling's or Bendix solution. What Fehling's or Bendix solution contain? Cupric sulfate, copper is in +2 state. Where that +2 state of copper of the Fehling's or Bendix is reduced to +1 state. Ultimately the product formed is cuprous oxide. What is the color of cuprous oxide? Red color. That's why in the earlier cases of detection of diabetes, doctors used to do a urine test. The urine sample is collected, blue color Bendix solution is added, just warmed on a spirit lamp. If the urine contains sugar, if kidneys filter sugar into the urine, sugar breaks into glucose plus fructose. Sugar is made up of 2 units, glucose plus fructose. Glucose contains aldehyde group. So this aldehyde group will reduce the Bendix solution, the blue color cupric sulfate solution, into red color cuprous oxide. Thus a sample of urine is tested positive for glucose or sugar with what reagent? Fehling's or Bendix. So what happens when Fehling's or Bendix react with aldehyde group? They themselves are reduced. Aldehyde group is oxidized to carboxylic acid. So here, so cuprous oxide is red. One more point here you have to know. This point we already discussed. I discussed that why KMNO4 is pink color, why potassium dichromate is orange color, why chromium peroxide is blue color, charge transfer. That applies to cuprous oxide also. The red color of cuprous oxide is due to charge transfer. Is due to, because Cu plus no unpaired electron, D10 configuration. So with the D10 configuration, cuprous ion with no unpaired electron, but why it is giving red color in cuprous oxide? The negative charge of oxygen is transferred to the vacant orbital of copper. It is called charge transfer. Because of charge transfer, cuprous oxide is red in color. See, there are many oxides here. Top oxide +7 oxidation state is Mn2O7. Write one more point. Mn2O7 is an acidic oxide. Generally metal oxides are basic oxides. But in metal oxides, if the metal is in highest oxidation state, they exhibit acidic nature for the oxide. So Mn2O7 is an acidic oxide because Mn is in its highest oxidation state. Write one more point there, Mn2O7 plus H2O. Mn2O7 plus H2O gives 2HMnO4, permanganic acid. Mn2O7 plus H2O gives rise to 2HMnO4, permanganic acid. You write V2O5 is an amphoteric oxide. ZnO is also an amphoteric oxide. ZnO, V2O5 are amphoteric oxides. Here some mixed oxides are mentioned. The star mark Fe3O4, ferroso-ferric oxide, FeO plus Fe2O3. Yesterday in your notes it is there. So the star marked are what? Mixed oxides. In mixed oxides, the metal will have fractional oxidation number. What is the oxidation number of iron in Fe3O4? Plus 8/3, we discussed yesterday. See try yourself. MnF7 is not stable, while Mn2O7 is stable. Because we discussed already this point. F cannot bring highest oxidation state, but oxygen can bring highest oxidation state due to the formation of p pi d pi multiple bonding. Due to the formation of multiple bonding. What is the hybridization of Mn in K2MnO4? Plus 6, they are asking hybridization. Plus 6, 3D 5, 4S, 3D1 actually, 3D5, 4S2. You remove 6 electrons. You will get 3D1, 1 electron left there. But MnO4 2 minus is tetrahedral. Anyhow, we have to refer that. We can't predict. Put a question mark. Why is FeI3 not stable? At this point, we already discussed in PbI4. Why PbI4 does not exist? It is there in your notes. Same principle applies here. Correct. So in PbI4, Pb in plus 4 state is a strong oxidizing agent. I minus is a good reducing agent. They both undergo mutual redox reaction and form PbI2 plus I2. Same reason. Example 9 we discussed already. Ruthenium and osmium show plus 8. In ruthenium tetroxide and osmium tetroxide. This point today we discussed, explain the irregularity in the above values. The E0 values are not regular, which can be explained from the irregular variation of ionization enthalpies and also the sublimation enthalpies. Sublimation enthalpy is nothing but enthalpy of atomization, which are relatively much less for manganese and vanadium. Why the E0 value of Mn3 plus / Mn2 plus couple is much more positive than Cr32 plus Cr2 plus or Fe3 plus / Fe2 plus explained. So this you have to write. Please write, this is the last why is the E naught value for Mn3 plus Mn2 plus couple is much more positive than that of Cr3 plus slash Cr2 plus or Fe3 plus slash Fe2 plus? Explain. The answer, much larger IE3 of manganese. This answer is much larger IE3 of manganese. Within bracket D5 to D4. This already we 8.4 table we discussed already. So like this we will go page by page and see any point related to your NEET examination. We will discuss that point. You can also make a note of it. Like that we will continue. Okay.